Alright, this is something we didn't do last year. What if we had a whole bunch of projectiles hitting something? So, like bullets hitting a target, for instance. What if, every time it hits, you get some force, right? Because the momentum of this one little tiny bullet would have to be changed because it was moving to the right and then hits the target. It can't continue moving to the right, the target's in the way. So some sort of momentum change will have to happen for every single little bullet. And I want to know, what kind of force does that put on the target? Okay, now to keep any kind of like weird kinematics things from happening, because if you hit the target, there'll be a force on it, so it'll start to accelerate backwards. I'm bolting it down. Okay, so it's not going to go anywhere. Alrighty. So we want to figure out what the average force is on this target. Like, it wouldn't be too hard to find out what the force is for each little bullet, but when I'm being hit by bullets, I'm not really concerned with each individual one. I want to know the overall effect. So something we're going to switch to help us out with this one is impulse, which we've talked about before. It's the change in momentum. We're going to start calling that by a variable that is a capital J. Okay, capital J. This is on your, I think this is how it shows up on your AP like cheat sheet they give you for the test, so we're going to start using it. Okay, so let's say that the impulse J for this particular problem that's the change of momentum of the target. Okay. We're also going to say that the total, we're going to say each, oops, come on, there we go. We're going to say that each bullet undergoes a change in momentum of delta P. Okay, so delta P for each bullet. I should be calling them projectiles, but you know what? It's easier to write bullet. So that's what I'm going to call them. Okay. We're also going to say, we're going to use this letter N. N you've probably used in math class many, many times. It is a generic number, usually unitless. Actually, it's always unitless. So in this case, N is going to be the number of projectiles, or number of bullets, okay, that collide in a time interval delta T. Okay. Now, that means, if I put these together, then the change of momentum that's happening in an interval of time delta T would be, let's see, delta P times N. Okay, because N is the number that happens, and we have delta P for every single bullet. Now that's the amount of change, like, of the bullets. I want the change momentum of the target. So the bullets were moving to the right and are probably going to stop or bounce to the left. Whatever they do, the target's going to do exactly the opposite. So I actually have to put a negative in here. Okay? So what I end up with is the change momentum of bullets in a time delta T would equal the same magnitude change in the target, but just the other way. Okay, I hope that makes sense. I'm gonna just rearrange that so that I have the J in front. I'm not doing anything special. I'm just writing it the other way, and I'm changing the negative to be on the other side. That's all I'm doing for that. I also know from last lecture and also last year that impulse equals average force. So this would be the average force on the target times time, and that's really delta T, so the time interval we're talking about. Okay, now if we put these two together, let's go back to black. Okay, if I put these two together, and I'm gonna move on to the next page here, what I get is, let's see, negative N delta P, where delta P is the change in momentum of every single bullet, equals the average force exerted on the target. So if you were the target, basically this is what you'd kind of feel at any given moment, times the time interval. If I rearrange that for the average force, because again, that's what I would be concerned about if I was being hit by bullets, is how hard am I getting hit? You know, will I be okay in a vest, or a bulletproof vest or something? Okay, if I arrange this, then I get negative n. Let's see, negative n delta p. Oops, I shouldn't have squished that much. I'm sorry. Okay. Okay. Now, actually, I can even take delta p and break it down a little bit more. So I get negative n. Delta p, when you look at momentum is m times v. Well, m isn't really going to change, is it? I mean, unless the bullet, like, pieces break off of it, but then the math just gets so crazy. We just don't do problems like that. So what we're really saying is negative n times m times the change in velocity, because velocity is really the thing that's changing to make momentum change. Okay, so this gives us F, the average force that you'd feel as a target in terms of, well, number of bullets divided by delta time. That's the rate at which the projectiles are colliding with the target. Okay, so right there, if you are given right there, if you are given like bullets are fired at a rate of 100 bullets per second or something, right there, that's what they're talking about. You've got 100 bullets per second. That's what they're talking about. And then over here, change in v, it depends on what the projectiles did. It's probably going to be in a problem, whatever problem it's give you. For instance, if, example, oops, forgot the E. For example, if your projectiles like stopped on impact, so they hit it and they like went thunk, and then like fell down or something, then we can, for delta V would be, see, it'd be your final velocity minus your initial velocity, which if they're stopping, your final velocity is 0, and then minus their initial velocity. Okay, so basically the change would be negative initial velocity. Okay, now, and then you just stick that in there right there. Sometimes they'll give you problems where, another example, like I'm pretty sure I gave you a homework problem about bullets bouncing off of Superman's chest, and I think in that one that the problem said that they bounce off. They rebound directly backwards from the target with no change in speed. In that case, your final velocity is exactly the same but in the opposite directions of as your negative velocity. So in that case, delta V would be, let's see, it'd be V minus V naught, which, well, V is negative V naught, so what you have is negative V naught minus V naught. What you have is negative 2 V naught, okay, for your change in velocity. Okay. Now in my book, they have another way that we can write this black equation here. I find this one the most useful because in almost all the problems that we do, they give you the rate of fire of something, rate of fire of a gun or whatever. But we can also rearrange this to say, hey, what about the average, the average force on the target if you're given the rate of which mass collides with the target? So maybe, I don't know, maybe they don't tell you the size of the projectiles or something, and they just tell you like how much mass is hitting the target or something. In that case, the change of mass is really how many bullets are colliding times how much each bullet's mass is. So you can replace this n and this m with delta m. Okay, so that would be negative delta m over delta t, and then I've still got my change in velocity over there, which we've already talked about. Now again, I don't really like this one. I don't use it much, but again, this is average average force on the target in terms of this delta m over delta t, that would be the rate of change of mass, which is the rate at which mass collides with the target. Okay. Again, not so useful. This is the one you really want up here. Let's see. How about some yellow right here? This average force that a target would be feeling is equal to the rate of negative rate of fire times the mass of each projectile times the change in velocity of each projectile.